All right, this is going to be number 62. And in number 62 it says, comets move around the sun in very elliptical orbits. At its closest approach in 1986, Comet Halley, right here in 1986, was at a distance, or perihelion distance, of 8.79 times 10 to the 7th kilometers. Remember, the closest point is what's called perihelion. And its velocity at perihelion was this. So we know how close it was and what its velocity was at that point. Now, Comet Halley has a 76-year period. So it goes way out here. It actually crosses over the orbit of Neptune, comes out here, and then it free falls all the way back in. What we want to find here is this: what is the comet's speed when it crosses Neptune's orbit? So we want to know what its velocity is at that point right there. Now, the bad news is, it's not at perihelion. If it was at at aphelion point, the furthest distance away, if it was, we could just do conservation of angular momentum. This would be very easy. But the problem is it's not there, it's before that point. We can't do conservation of angular momentum because the velocity vector at this point is this way, the radius vector is this way, and we have no idea what that angle is in there. And remember, angular momentum is equal to mvr sine of the angle. Well, if you don't know the angle, you can't get the angular momentum. Okay? Here we could get the angular momentum because the velocity is this way, and the radius vector is that way. It would be 90 degrees, sine of 90 is just 1. So that makes it very easy. That's why you can do it at perihelion, and you can do it at aphelion. But we can't do it this one because we don't know that angle. You can try to calculate that angle, but it would be a challenge. Okay? So how are we going to do it? We're going to do it as energy. Because in an orbit, remember, both angular momentum and energy are always conserved. So we're going to say energy initial is equal to energy final, or that energy at any point in its orbit is going to be the same. The total energy charge is going to be the same. It's always going to be equal to kinetic energy plus the gravitational potential initial has to be kinetic energy final plus gravitational potential final. So that's what way we're going to solve it. So we're going to look at this and we're going to say, okay, its initial point is when it's here. Well, its kinetic energy is just 1/2 its mass of the comet, times its velocity at perihelion squared, minus, remember this is always minus, g, mass of the sun, because that's what it's orbiting, mass of the comet, over the radius at perihelion, its distance at that point. That must be equal to 1/2 times the mass of the comet times its velocity at Neptune's orbit, I'm going to call it Vn squared, minus g, mass of the sun, mass of the comet, divided by the radius of Neptune's orbit. All right, so all I did was fill in what the kinetic energy and the gravitational potential was at each of the points. Notice we can divide through by the mass of the comet. It doesn't matter what the mass of Halley's comet is. That goes away. Okay? We know this stuff over here. This is a constant, right? What we want to do is solve for the velocity at Neptune's orbit. So I'm going to move that to this side over here. I'm going to rewrite it with this side on here. So I'm going to have 1/2 the velocity at Neptune squared. Right? I'm going to write that over here. I'm going to move that to this side. This becomes 1/2 the velocity at perihelion squared minus g, mass of the sun, radius perihelion. That becomes positive g, mass of the sun, over the radius at Neptune's orbit. Now, I'm going to multiply both sides by 2 to get rid of that. Multiply the whole thing by 2. So I get the velocity at Neptune's orbit squared. Well, if I distribute the 2, it looks like I'm squaring it. I'm multiplying by 2. That goes away, so this becomes velocity of perihelion squared. And then, look, I got a GMS in both these. I can take that out. So I'm going to do this as plus, right, 2 times GMS, right? If I factor that out from those, this is going to be minus 1 over radius at perihelion plus 1 over the radius at Neptune. Now I know I did about 2 or 3 steps all together there. If you don't understand that, just write it out to see what's going on. But I multiplied both sides by 2, and I factored out the GMS for these two terms. Okay? I still have minus 1 over RP and plus 1 over RN here when I factored this out, and then I multiplied that by 2. The 2 canceled with the half. So that's how I ended up with this one right here. All right, now I just take the square root of the whole thing, and I get the velocity at Neptune. So the velocity at Neptune is equal to the square root, and then I just got to put all these numbers in. Notice though, I have to put them in the right units. This is in kilometers per second. So this is 54,600 squared plus 2 times 6.67 times 10 to the minus 11. Now we have to do the mass of the sun, which is around 3 times 2.9. Now where am I at here? Where's the mass of the sun? Mass of 1.99 times 10 to the 30th times this minus 1 over the radius of perihelion, which is 8.79 times 10 to the 10th. Notice that this is in kilometers, I wanted in meters, so I multiplied that by 1,000 plus, and this I have to look up. I had to look up what the radius of Neptune was. And the radius of Neptune, at Neptune's orbit, is 4.5 times 10 to the 12th. All right, get all that? All right, don't worry. This is not going to be a negative number. You're not going to take a square root of it because this is going to be smaller than this term here. When you come through, I should say, this whole term is going to be smaller than this term right here. All right? And when you solve all that in your calculator, you get the velocity when it's at Neptune's orbit is 4,418 meters per second, or 4.418 kilometers per second, which is a few extra significant figures, but that's okay. So it went from 54 kilometers per second to 4 kilometers per second when it gets out to this point up here. And that's how you do it. And you can't do it as conservation of angular momentum because you're not at aphelion point.